In this video, we will begin our discussion of integration by parts. Integration by parts is going to be our first more advanced method of integration. And if we think back to substitution, it undoes the chain rule of differentiation. In a very similar fashion, integration by parts is going to be a method of integration that undoes the product rule of differentiation. So recall what the product rule tells us, right? The derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. And what I'd like to do is take this differentiation formula and turn it into a formula for anti-differentiation. So I'm just going to go ahead and integrate both sides. And on the left-hand side, remember that when we integrate a derivative, those two things actually cancel out. So that goes away. So we would have f of x times g of x is the indefinite integral of f prime g plus the integral of f times g prime. And what I'm going to do here to get a formula, and this will become more clear in a moment, is I'm going to go ahead and just solve for this integral we have on the far right. So what this gives us is that the integral of f times g prime would be equal to what we have on the left-hand side already, f times g, and then we're going to have to take this other term and subtract it over. So minus the integral of f prime g of x. And this formula is typically what we are going to think of as integration by parts. So to summarize, the general formula for integration by parts is the exact formula we had on the previous page, but oftentimes it's more convenient to think of the function f being u, the function g being v. So we would have the integral of u dv equals uv minus the integral of v du. And this form is typically much easier for us to apply and commit to memory. The integral of u dv is uv minus the integral of v du. And we'll see this in action in a moment, but before looking at a few examples, let's just make a couple observations. So some key observations. Integration by parts does not solve the integral. Much like a substitution, what it does is it takes a potentially difficult integral and expresses it in terms of a simpler, easier to evaluate integral. In order to evaluate, we somehow have to look at our integrand and choose the u and the dv. And a couple rules of thumb that will become more apparent as we practice examples. We need to choose u and dv in a way that dv is something we can anti-differentiate, so we can go from dv to v. And ideally, we choose u so that du becomes simpler. If it's a definite integral, we just throw in the appropriate limits of integration. And the big question you might be wondering is also, when do we apply integration by parts? The typical examples will be x to a power times cosine or sine, x to a power or a polynomial times an exponential times a sine or a cosine, and then any type of inverse function, arcsine, arccosine, arctangent, natural log, etc. Also, depending upon the function f of x, things of the form x times f of x will be well suited for integration by parts. And we will see examples of each of these types of integrals. So we begin with the indefinite integral of x times e to the x. We're going to go ahead and apply integration by parts. And when we apply integration by parts, what we need to do is come up with a u and a dv. And let me remind you the formula for integration by parts. The integral of u dv is equal to uv minus the integral of v du. And what we need to do is choose dv to be something we can anti-differentiate, and ideally we want to choose our u in such a way that du becomes simpler. If we look at our choices, x and e to the x, only one of those things really becomes simpler when we differentiate, the x. E to the x just remains the same. So if we let u be x, that means dv needs to be e to the x dx. And just as a side note, whatever we choose for u and v, dv, when we multiply these together, we need to get exactly the integrand. So now we calculate the two other things we need. Du would be 1 dx, and v would be the antiderivative of e to the x. So e to the x. Integration by parts tells us that this integral will be equal to uv, so x e to the x. Then we subtract away the integral of v du. So we subtract away the integral of e to the x times 1 dx. So as mentioned, integration by parts does not solve the integral, but what it does is expresses it in terms of an integral that we can evaluate much more efficiently. So the x e to the x comes along for the ride. The antiderivative of e to the x is e to the x. So we very quickly have our antiderivative. As a side note, if the x that we had in this original integral was instead a different power of x, we could still use integration by parts. So integration by parts also works well when we have x raised to any power, or in fact it could even be a polynomial times the exponential. So a second example that has a very similar form to it, we have x times a function. And when we have x times a function, it's reasonable to try integration by parts, just like we did in the previous example, by letting u be equal to x and dv being the remainder of the integrand. So let's try it. We'll let u be x and dv be sine x dx. So we need to be able to anti-differentiate sine to get our v, so minus cosine, and differentiate dx to get our du. So du is simpler dx. Integration by parts tells us uv minus the integral of v du. So this integral becomes minus x cosine x minus the integral of minus cosine x dx. So the minus pulls out front, and this becomes a plus. And then we have the antiderivative of cosine. The antiderivative of cosine is sine, which gives us the desired indefinite integral. And once again, kind of a key observation we can make, if instead of having an x, we had something like x squared, even x cubed, this would also be something that we could very reasonably solve via an integration by parts. We just might need more than one integration by parts.